The General Center Theory by Dr. Alon Giladi. Article 1. Toward the Fourth Leap of the Way.
When we observe mainly modern thought, which is the scientific and technological issue, when the moral and faith issue have been neglected and have deteriorated and gone from era to era to era, we see confusion, we see error. Along with the accelerated technological development, in the various levels we see, in terms of the leaps and bounds of the scientific world, some kind of confusion, some kind of dead end, from which scientists are unable to get out and are actually digging themselves into it with theories upon theories that are proven wrong repeatedly. If we look at some kind of simplistic and broad spectrum at human thought in the scientific theoretical field, then we see, in a simplistic way, 3 leaps forward. The first leap forward is Aristotle's breakthrough. It is the breakthrough of Aristotle's Greek logic from the field of science, from the field of theoretical science, with Aristotle as the scientific leader, laying the foundations for theoretical, observational, experimental, logical thought. And when we look at the next leap that followed him, which was made not a year or 2 years after him, we see Isaac Newton's leap. That leap whose well-known motif, not exclusively, is the theory of mechanics. This well-known matter also fits well with the developing philosophical views of his time. The views of Descartes, Spinoza, and so on, about some kind of world that runs like some kind of clock, not without God, or a God who is supposedly identified with nature, according to Spinoza, but some kind of mechanism which operates like a clock. In a logical way, which is nature's language, Isaac Newton discovers his 3 fundamental laws that are still used by us today, certainly within certain limits. The first law is the law of inertia, according to which everybody continues in its state of rest or in its state of motion in a straight line as long as it is not resisted by forces imposed on it. The second law is the law of acceleration, meaning that the acceleration of a body is always proportional to the force exerted on it, or according to his well-known formula. F, force, equals m, mass times a, acceleration. The acceleration of the body will always be proportional to the force exerted on it, and in the same direction. And if there is more than one force acting on a body, then the forces acting together must be combined to understand how the body acts into a vector sum to the equivalent force acting. And Newton's third law is the law of action and reaction, meaning that when we exert a force on a certain body of a certain mass, it will exert the same force in return, and this force will act on the straight line that connects the body on which we exerted a force and the body that exerted the force. One of the central motifs in Newton's thinking is the motif according to which mass exerts a force on another mass, meaning that one star exerts a force on another star. But this is the force of gravity as we know from Galileo's experiment, and later. That is, anybody at low speeds that falls on Earth falls at exactly the same acceleration as another body. Of course, as a result of the mass differences, there is a different resistance from the air, and so on. But if we take a feather and a stone and drop them in a vacuum to the Earth, they will arrive in front of the Earth at exactly the same time. The formula for Newton's gravitational force is force equals g, the universal constant of gravity, times m1 of one mass, times m2 of a second mass, divided by the radius, divided by the distance squared between these two masses that are relevant. Well, Newton saw the world mechanically. He saw the world as a world in which there is constant space and constant time, but he did not explain what gravity is. Newton's formulas are excellent formulas until you reach extremely high speeds, until you reach the subject of light, which he actually did not take into account within the framework of his theory, within the framework of the theory of mechanics, or in other words, Newton's world was a mechanical world, so-called deterministic, in a constant way, in an absolute way, that relativity did not enter into it. After Newton came the third leap forward in the scientific world, when we observe it in a simplistic way, and it is the leap forward of Albert Einstein. Einstein introduces into the observation of nature the subject of light, the subject of observing time as relative time, the subject of observing space-time according to his method, which turns Newton's theory upside down under extreme conditions. Newton's theory continues to be accurate up to a certain limit, up to the limit of light, up to the limit of the speeds of light, up to the limit of the extreme cases of black holes, of the Big Bang, and so on, up to the limit into which Einstein's theory supposedly enters in order to correct Newton and to complete it. Well, according to Einstein, who discusses energy, which Newton doesn't really address, energy and mass are equivalent to each other, dependent on each other, curve space-time, meaning it's not that there is a force of one mass, a gravitational force of one mass on another mass, according to Newton, but rather that it is some kind of curvature of the concept of space-time by the mass and by the energy that creates the force called gravity, which in fact is not a force, but it is some kind of curvature of space-time to which the various bodies are attracted. One of the most prominent proofs of this claim is that we see that light bends near the black hole, meaning that light should have been a straight line, as long as we are talking about gravity, because gravity apparently does not affect light that has no mass. But we see that light bends near the black hole, meaning that apparently this is proof that space-time is the one that bends, and not that there is any gravitational force. The reason to this claim is that in a black hole, which is actually a singular point of some star that has collapsed into itself, what we would expect in that situation is that light would not bend near it, but would be swallowed into it in a straight line. And this is apparently not what we see. Well, according to Einstein, time is relative, space is relative, according to a point of view in relation of mass that is at a higher speeds relatively to another mass. And as near as one gets to the speed of light, which is the highest speed in nature, the relative difference gets bigger in a higher significant manner. Einstein's well-known formula for these claims is E equals mc squared. In the framework of his special theory of relativity, this means that at such high speeds, time is lengthened in relation to the observer who is at lower speed. The time of the one who is near the speed of light as time passes much more slowly than the time of the observer who is at lower speed, and so is the other way around. Space is shortened significantly for the one who is at near the speed of light, compared to the one who is at lower speed. Although in the framework of Einstein's 4 breakthrough papers from 1905, he was required, among other things, to the special theory of relativity. He was required to develop his theory to the general theory of relativity from 1915. Here, Einstein attended to the issue of the exchange between Newton's gravitational force and his new claim of curvature of space-time. He attended to it within the framework of the formula that also included the reference to the speed of light in this context, which includes, among other things, Newton's universal constant, g. But it adds to it the reference to light, that is, the tensor of space-time. The tensor of the curvature of space-time equals 8 times pi times the universal constant g, divided by the speed of light, c, to the power of 4 times the tensor of kinetic energy. Einstein arrived to this complex formula in an extremely complicated way, a matter that took him about 10 years while consulting mathematicians and the like. But Einstein's theory was also met with a problem, just as Einstein encountered a problem within the scientific theory of his time. a problem that was solved with all sorts of means, such as the claim that light cannot propagate in a vacuum, and therefore they claimed that there was some element in the name ether on which the electromagnetic waves are carried, and the like. After Einstein's theory of relativity, this matter of the ether as a carrier of electromagnetic waves and the like fell out of. And if we look at the observation today of Einstein's theory of relativity and its failures, we see some kind of attempt by scientists to invent something again that has no proof and that still serves them because they are unable to resolve the contradictions in the framework of the theory of relativity, mainly in three main ways. The first problem is the problem of singularity. That is, Einstein's theory collapses when it attends to the center of the black hole. That is, to the same point to which the star collapsed after a supernova, which is a point that attracts all matter so extremely that not even light can escape from it, and therefore this phenomenon is called a black hole. The second problem of Einstein's theory is the problem of quantum mechanics. In other words, Einstein's theory of relativity does not fit with what we see apparently in the behavior in the smallest dimensions, which is in the dimensions of the elementary particles of the universe, in the dimensions of electrons, in the dimensions of quarks, in the dimensions of gluons, and not long ago, some elementary particle was added to the quasi-superposition like the Higgs particle, which some have called the divine particle, and claims that gave mass to electrons and quarks. Unlike gluons and photons that have no mass, that are particles that carry energy, unlike other particles which have mass and the potential for energy in it. And the third main problem that Einstein's theory does not fit with is the problem of the expansion of the universe at an accelerated rate. That is, why is the universe not falling apart as it should have been according to the relativity theory? Einstein's theory of relativity does not provide an explanation in the fundamental aspects of the universe, and scientists have tried to explain it in all sorts of different ways, including by claiming that there is some kind of dark matter or dark force that fills the entire universe, that we do not see, that they are not observed, that they are the ones that stop the universe from collapsing, which was supposed to happen according to Einstein's theories. This and more, the conventional science finds it necessary to add some additional constant that no one knows to this day in order to explain the development of the accelerating universe, which is expanding at an accelerated rate. The theory of relativity, which is a classical theory, does not work in the framework of small particles. When a particle behaves like a wave, it is seemingly impossible to predict exactly what will happen and where it will be, whether it acts as a wave or as a particle, whether it can supposedly be in the same place at the same time, whether it may be characterized as a wave but not as a particle, and so on. There are fundamental phenomena that seemingly cannot be explained, and to this day have not really been understood, certainly not within the framework of Einstein's theory of relativity. Moreover, these phenomena actually constitute a contradiction to the theories of relativity. Well, if we look at scientific breakthrough, scientific leaps, we see that every scientific correction stems from some kind of anomaly, from some kind of error, from something in our observation of the universe that doesn't fit with that theory. There are periods of time when between one breakthrough and another, we try to somehow force what we see into the existing theory, into the convention, but that's exactly what we're not willing to do within the framework of rational theoretical thought, within the framework of scientific theoretical thought, which is thought that constantly requires questions, constantly doubt, and constantly progress through refutation, proof, and refutation.